Welcome to qnawire.
Hi, so in this case what we want to know is the bond length in between hydrogen and bromine in HBr given the rotational spectrum that tells us that each of the lines are separated by 16.72 centimeters to the minus 1. So first of all, let's remember that in the rigid rudder approximation, the energy of the rigid rudder is going to be equal to B times J plus 1, where B is equal to h bar squared over 2 times I. Other thing that we know is that in the case for a diatomic molecule, the moment of inertia is equal to the reduced mass times the bond length squared. And the reduced mass is going to be equal to mass 1 times mass 2 divided by the sum of each of them. Now, by using these formulas, we can know that the difference of energy in a rotational spectrum is going to be equal to 2 times B times J plus 1. Furthermore, we can directly express this in terms of frequencies as follows. If we divide this expression by h times c, remember that energy is equal to h times nu, and if we divide this by h times c, what is going to happen is that h and h are going to cancel out. Frequency has units of centimeters to the minus 1, so what is going to happen here is that our final units are going to be wave numbers. So with this, we can write down, knowing that the possible transitions are for j equals 0, 1, and so on. So we set j equals 0. If we divide delta E over hc, this is going to be equal to 2 times v divided by hc. And over here, the only thing that we need to know is how to isolate the bond length. So on the left hand side, we're going to put the value of the wave number, centimeter to the minus 1. For this, what we're going to employ is using the units of C of centimeters per second, just to get the result directly. And instead of B, what we're going to write down is this constant over here. So this becomes 2 times h bar, that is equal to h over 2 pi, all of this is squared, divided by 2. So 2 and 2 are going to cancel out, and over here we're going to have 1 over I. And we have from the left hand side the 1 over hc. So the result now becomes that 16.72 centimeters to the minus 1, the wave number, will be equal to h divided by 4 pi squared times c times moment of inertia. So over here, 8 pi squared times c times moment of inertia. And this now becomes h divided by h times pi squared times c. The moment of inertia, we said that was the reduced mass times the bond length squared. So solving for L squared, let's call this constant. So solving for L squared, we're going to get L is going to be equal to the square root of h divided by 8 times pi times c times mu times the value that we found, 16.72 centimeters to the minus 1. And over here I forgot the squared. So now just replacing the values, L equals to the square root of 6.63 times 10 to the minus 34 joule second divided by 8 times pi squared. The value for C is equal to 2.99 times 10 to the 10 centimeters over second, multiplied by 16.72 centimeters to the minus 1. And finally, we need the value for the reduced mass. And the reduced mass, we can calculate it. First of all, we can do the calculation in atomic units, and then we're going to transform that into kilograms. So the reduced mass, we said that was mass 1 times mass 2. So mass of hydrogen times mass of bromine divided by mass of hydrogen plus mass of bromine. In this case, this is going to be 79 divided by 80 atomic units of mass, with a plus over here. So the result is 0.9875 atomic units of mass, or UMAs, depending on which country you're on. And this corresponds to 1.64 times 10 to the minus 27 kilograms. So we can replace that value here, 1.64 times 10 to the minus 27 kilograms. And with this, our final answer for the bond length is 1.01012 times 10 to the minus 10 meters. And this is the same as 1.012 angstroms. And that would be all. A few comments over here. You can technically just go directly and use this formula, but this is the explanation of where that formula comes from, and the reduced mass, as one would expect, is closer to the mass of the hydrogen, because in the effective system, it is like the hydrogen is moving and the bromine is staying almost on its place during the whole procedure. So this is the final result. Thank you very much and have a good one.